In this enhanced model, the objective of the controller is to regulate engine speed with a force throttle actuator such that changes in the load torque have minimal effect. This is easily accomplished in Simulink by adding a discrete time PI controller to the engine model. We choose a control law which uses proportional plus integral control. The integrator is needed to adjust the steady state throttle as the operating point changes, and the proportional term compensates for phase lag introduced by the integrator. Here we are using closed loop model. Here is the equation. N set is the speed set point in RPM, and Kp is the proportional gain, and Ka is the integral gain. Let's simulate the model. Here is a speed set point. Here is the controller having a desired RPM and speed and input, and output as a total angle. I'm going to connect the here I'm connected the speed set point to the desired RPM. Here is the throttle manifold. The output of this throttle angle I'm going to give into this as input. And in this the engine speed is connected, the combustion speed also connected, and it goes to the crank speed is in radius per second, and the engine dynamics output is given to this, and the engine speed is given to the scope. And here the combustion torque and the load torque is given to the engine dynamics, and the simulation output is the combination of throttle angle is in controller, and the load torque value given to the simulation inputs, and go to the scope. In this model, we employ a discrete time controller which is suitable for microprocessor implementation. The integral term in equation 1 must be realized with the discrete time approximation. As is typical in the industry, the controller execution is synchronized with the engine crankshaft rotation. The controller is embedded in triggered subsystem that is triggered by the valve time signal described above, and the detailed construction of the control subsystem. This block implements a This block implements a proportional integral control system in discrete time. Note the setting for a sample time set internally at -1. This indicates that the block inherits its sample time. In this case, executing each time the subsystem is triggered. The key component that makes this is a triggered subsystem is the triggered block. Any subsystem can be converted to triggered subsystem by dragging a copy of this block into the subsystem diagram from the Simulink connection library. The figure 2, which is shown on the screen, is a speed controller subsystem. Just run the Simulink. It's compiling, and after completion of the compiling, just click the scope of the engine speed to know the engine timing model graph. Just click on the scope. Here is the output of the engine speed with respect to the time. Typical simulation results are shown in this screen. The speed set point steps from 2000 to 300 rpm. Rt is equal to 5 seconds. The torque disturbance are identical to those used, and just note the quick transient response with zero steady state error. Several alternative controller tunings Ki and Kp, and these can be adjusted by the user. And here is the value shown for Ki and Kp. You can also adjust the value of the Ki and Kp. Just an Excel sheet. And the conclusion, the ability to model non-linear complex systems such as engine model described here is one of the Simulink key features. The power of the simulation is evident in the presentation of the models above. And the Simulink retains model fidelity and including precisely timed cylinder intake events, which is critical in creating a model of this type. The complete speed control system shows the flexibility of the Simulink. In particular, the Simulink modeling approaches allow a rapid prototyping of the interrupt-driven engine speed controller. Here shows the model of the closed-loop simulation result, which is also shown as a result in the simulation. The engine speed in RPM is an y-axis, and the respective time in second in x-axis. That's it.